All right, Chapter 9. We are going to talk about gases in this chapter, and we're going to start off by talking about the general properties of gases, which is something we considered in an earlier chapter in this class, but we're going to come back to it now. So number one, gases expand to completely fill their container, and then by necessity, they must also then take the shape of their container. So if you take something that is under vacuum, and you put a little bit of gas into that thing that is under vacuum, that gas will actually expand to fill the container. This does not mean that you're going to make more gas in doing this. It just means that the gas is going to evenly distribute itself around that container, and therefore, by necessity, take the shape of that container. Gases also tend to be very low density, much less than solids or liquids. Solids and liquids tend to have significantly higher densities, whereas gases are also compressible, unlike liquids or solids. Liquids and solids tend to maybe compress just very, very slightly if you put a lot of pressure on them. Solids not quite as much. Really neither one of them do it very much, but sometimes you can get them to compress a little tiny bit, but gases are very compressible, and quite easy to compress, actually. They also tend to, but they always will form homogeneous fluids if you have a mixture of them, which is to say that you're not going to have gases that separate out once they've been mixed, anyway. You can have two different gases if you introduce them into the same container very carefully. They will kind of stay separate for a little while, but eventually they will form a homogeneous fluid, always. And especially if you intentionally mix them. If once you have them mixed, they're not going to go back to being separated, ever. The theory that we're going to use in this chapter to try and describe how gases work is called the kinetic molecular theory of gases. And this is made up of actually 4 different parts. One of them is missing here. I'm going to write it on the screen in just a second. But this theory of how gases work is all based on what is actually happening at the molecular level with these gases. So the first part of this theory is that gas molecules are in constant motion. Gas molecules never stop. They never have to stop and catch their breath or just decide to change directions or anything like that. They are constantly moving, and they only stop moving for the very split second when they collide with something else and get bounced off in a different direction. So they never really stop moving. They just move until they hit something, and then they move until they hit something else, and then they move until they hit something else, and they just keep doing that for the rest of time until they react with something and are no longer a gas. The speed of gases is also related to its temperature. So as you heat a gas up, gases will move faster. The molecules in the gas will move faster, and when you cool gases down, they will move slower. In addition to that, gas particles neither attract nor repulse each other. And this is where we're actually getting into some assumptions here. These first 2 parts here, the statement that gas molecules are in constant motion and that gases increase in their speed as you heat them up, those are absolutely true. There's no exceptions to these 2 rules. But this third part of the theory here is actually an assumption. It's not 100% true. So the assumption is that gas particles neither attract nor repulse each other. Essentially, they're like pool balls. They just kind of move in a direction, and maybe they'll hit something, but there's no magnetic forces or electric forces or anything that are pulling gas molecules together or pushing them apart. They're just neither attracted nor repulsed by each other. And that's not 100% true, like I said, but we'll talk about that more later. For now, we're going to go ahead and assume that it is 100% true. The last assumption here that for some reason got left out here, so I'm going to go ahead and put it in, is that gas particles occupy no volume. So the reason we're making this assumption is that it's pretty close to true. Like the actual particles of a gas are incredibly tiny compared to the volume of space that the gas is occupying. So you're sitting in a room right now. It's probably a medium-sized room, assuming you're not watching this in a closet. You're sitting in that room. There's gas in the room with you. You could probably take all the gas in the room that you're in right now, and if you compressed it to where it was the same density as a liquid, I have no doubt it would fit into a soda can. Like you could compress all the gas into the room into that small, very, very small volume, like less than 1% of the volume of the room, and is actually physically occupied by the gas molecules. And so because it's such a tiny percentage of the overall volume of the room, we just go ahead and ignore it. We ignore the fact that the gases do occupy volume, and the main reason we're doing that is it's going to make the equations that we use to quantify information about the gases a lot easier to deal with. It gets more complicated if we have to take the volume of the gas into account. Not crazy complicated, but complicated enough that we are going to ignore it for our purposes, for now, anyway. Like the first assumption here, we will come back to this later and discuss the implications of making that assumption. But for now, we're going to go ahead and assume that the particles aren't attracted or repulsed by each other, and we're going to assume that they don't occupy any volume. All right, let's talk about what's actually happening at the molecular level. The main thing that we're going to be using to investigate gases, or at least the new thing that we're going to be using to investigate gases, is the pressure of a gas, which leads us with the question, what is gas pressure? Essentially, what gas pressure is it's the actual physical force of the gas molecules smacking the walls of the container. So if you remember from the previous slide, the gas molecules are in constant motion. They are moving pretty quickly around, even when they're fairly cold. They're still moving around fairly quickly. And when they hit the walls of the container, there is a force that is applied to the container because of that. Even though they are tiny, tiny, tiny little particles, they do still have mass, and they're moving pretty fast. And so they smack the walls of the container, and there's an amount of force that goes along with that. And even though one of these collisions doesn't really apply any significant amount of force, there are trillions and trillions and trillions of these collisions every second inside the container. And so even though just one collision is not much force, when you add them all together, you can actually get quite a lot of force. As we'll talk about later, atmospheric pressure is actually a lot of pressure. 1 atmosphere of pressure, which is what you're under right now, you're under 1 atmosphere worth of pressure. That is a lot of force. So this force, where the gas is literally just smacking into the walls of anything that it comes in contact with, this is happening constantly all around us and on us as well. It's happening to us. Right now, like I said, you are under 1 atmosphere of pressure, and the atmosphere is actually trying to crush you. There are trillions upon trillions of gas particles that are smashing into your skin, into your eyes, into in your lungs. There's constant bombardment of these gas particles, and they're hitting you with quite a bit of force. But thankfully, your body is actually made with a force that pushes back against that. This is why you see in the movies when people get sucked down into space, and they always show them like they start to bloat up. It's because you do actually have an outward pressure. Your body has a pressure pushing back against the pressure of the atmosphere trying to crush it. If it didn't, then you would actually be crushed. You can look up some videos on YouTube where people will take train cars, like actual whole steel train cars, and they will suck the air out of the airtight train car, and the train car will flatten like a pancake just from the atmosphere crushing it. So the atmosphere is quite a bit of pressure, but our bodies are made to withstand that. We have an outward pressure that's an equal amount of pressure so that we don't either expand or get crushed. We stay at the same size that we always are. And we actually have something that's pretty good at detecting pressure in our bodies, or more specifically, it's pretty good at detecting changes in pressure, and those are our ears. Our ears are actually really sensitive to changes in atmospheric pressure, which is why you can just go outside and drive up a big hill, and you can feel the change in pressure in your ears. The reason for this is there is a little bit of gas that is trapped behind your eardrum. And your eardrum is sealed shut, unless you're a little kid and you have tubes in your ears, which my kids actually had to have tubes, or at least one of them had to have tubes in his ears. But if you're an adult and you don't have tubes in your ears, your eardrum is sealed shut, and there's gas trapped behind here. And so if you have a certain pressure of gas behind your eardrum, and you have the same pressure of gas on the outside of your eardrum, atmospheric pressure, it feels normal. But if you drive up to the Rockies, and so you have Tulsa, Oklahoma, air pressure behind your eardrum, and the pressure is continuously lowering and lowering and lowering as you get higher and higher to higher and higher elevations, the pressure outside your eardrum will decrease and decrease, and so you'll actually have the atmosphere inside of your eardrum pushing on your eardrum. You can actually cause your eardrum to rupture if you're not careful, which is really bad. Which is why people tell you to chew gum or yawn or swallow or something like that if you're going in an airplane, or if you're driving up to really high elevations, because you want to equalize that pressure. And down here, somewhere in your sinuses, there's I forget what the name of it is, but there's some valve, or so it's not really a valve, but there's an area where if you contort your face just right, you can kind of pop for just a second, where there's enough space for the gas that's inside of your eardrum to equalize with the pressure outside. So somewhere down in here, so that gas, there's an opening there that goes down to your sinuses. Alright, so if we're not going to measure the gas pressure with our ears, because we can only measure changes, essentially, we can not really measure, we can just detect changes in pressure with our ears. Instead, what we're going to use is what's called a barometer to actually measure the pressure of the atmosphere. And the way a barometer works is you have a glass tube that is evacuated on the inside. So there's a vacuum inside of this glass tube, and you stick the open end of this tube down beneath a pool of mercury. So it's open down here below, and you have a vacuum up here above. So let's see here. Well, that's not working. Never mind. See if I can, there we go. So we have vacuum up here, and we have the open end down here, and the atmosphere because it's pushing on everything all the time, the atmosphere is going to push down on the mercury. Now, if the mercury has a place to go, it's going to go there. And so what happens is, because the atmosphere is pushing on the mercury and there's nothing inside the tube to push back, the atmosphere actually pushes the mercury up the tube. Now, the atmosphere isn't the only thing exerting a force on the mercury. Gravity is also exerting a force on the mercury. And so gravity is going to try to pull it back down. And so eventually those two forces equal out. So you have the atmosphere pushing down, which will then push the mercury up the tube, and then you have gravity trying to pull it back down. And wherever those two forces equal out, that is where you measure the pressure. And so we actually measure the atmospheric pressure by measuring how far up the tube the mercury travels. And in normal atmosphere, mercury will travel up this tube 460 millimeters. And so the unit that is used here is actually a very strange unit called millimeters of mercury. And so we have a few other units that we also use other than millimeters of mercury. The one that you're probably most familiar with is this one, pounds per square inch. This is kind of the American version. This is down here, this is the American version of millimeters of mercury. It's inches of mercury. For our purposes in this class, we are mostly going to use either atmospheres or torr. And torr is actually the same as millimeters of mercury. It's just they decided to give it a more sciencey sounding name than millimeters of mercury, because millimeters of mercury is kind of ridiculous. Excuse me. So all of these values here, all of these pressures are all equal to each other. So if at some point we need to do a conversion from one unit of pressure to another unit of pressure, these are the values we're going to use to do that. So 1 atmosphere of pressure is the same as 14.7 psi. And 460 torr, or millimeters of mercury, is the same as 1 atmosphere. So all these pressures here are equal to each other, and so that's what we'll be using to convert from one unit to another. Speaking of which, let's do a quick example here. So ignore the chapter number there, that is not correct. But if we look at the problem here, it says a high-performance road bicycle tire is inflated to a total pressure of 132 psi. What is the pressure in millimeters of mercury? So all we're doing here is the unit conversion. We're told that we have 132 psi is our starting pressure here. We're going to convert that value to millimeters of mercury. If we go back to our values here, 14.7 psi is the same as 760 millimeters of mercury, because again, torr is the same as millimeters of mercury. So if I put 14.7 psi on the bottom and 760 millimeters of mercury on the top, and then do that math. Actually, I don't remember what that is off the top of my head. I actually have to do that. So 132 divided by 14.7 times 760. That will give me 6,824 millimeters of mercury. Why is that not writing? Yeah. I must be on the edge of the slide there. It's annoying, I can't see it. Anyway, so that is millimeters of mercury. There we go. Alright, so if we were to actually hook that tire up to a barometer, we would have to have a 7-meter tall barometer to be able to measure that pressure with the barometer, which is a crazy tall barometer. But high-performance road tires like that are really, really high pressure. Really, really high pressure. Normal vehicle tires are something like 35 to 40 maybe psi, so this is much higher pressure. Alright, I think we'll end it there for this video. I will see you all in the next one.